It's on.
On now, right? Is it on? Yes.
Então, quem não se registrou, no caso do Hilário ali, né? Você pretende. Hilário, desculpa, né? O pessoal que quiser participar também desse concurso de extensão, tem um mínimo de frequência e no final tem um certificado que a gente tenta emitir pela universidade. O mini curso aqui ele já vai ter algum certificado de participação. Mas é possível ter pela universidade, só para dar. Não paga nada a inscrição, e já tem um link de inscrição e tal, se alguém tiver interesse, me fala que eu posso mandar o link. Tá bem? Bom, pelo sim, pelo não, vou passar uma presença aqui ao destino. Então, quem tiver registrado, quem quiser se registrar, já se inscreve, já anota aqui a presença, depois eu mando o link, tá bom? Talvez com o Leandro também seja interessante. E aí vai. Tá bom? Só para o pessoal, talvez para os outros não seja tão interessante esse tipo de certificado. Então segue a lista de presença, tá? Também tem interesse. Okay, let's start. So, good afternoon. So today, Selman will continue the mini course. Seems that he has some plan to, some schedule for today, and he will explain for you. Okay?
Okay, I'm told, please explain the elementary, explain to students. I think in order this thing to work, students should ask questions, talk to me. I'm here all day, sitting there by myself drinking coffee. There's nothing wrong just asking simple things, definitions. It's very natural when you're learning something. You know, nothing makes sense, and then you have to start somewhere asking questions. My father was a mathematician. I remember one advice he told me. There's this chewing gum. It's called shepherd's chewing gum in Turkey. It is most horrible thing. It is like a leather. You chew all day till your jaw drops with pain. But then at the end of the day, all of a sudden something happens. This turns into very nice, pleasant gum that you've ever seen in your life, with a nice aroma and everything. But you have to do it in your own time. Somebody else cannot do it for you. He told me math is like this. You have to keep looking definition, looking simple things, and then all of a sudden things will make sense. So, making a smooth algebraic. It's a closed smooth manifold. So this could be an embedding. I will explain the embedded case first. There are so many versions of this. One of the most misunderstood things I have found in this subject is, what is known, what's not known. I mean, Henry and I went proved all these theorems and published things. Then the first question we get asked, what did Nash prove, what did you prove, and what's a sheet, what is a component, who proved what? And after, we first try to understand Nash. I mean, there's the theorem by Nash, and then there's a Tognoli. Nash proved it, every smooth manifold is a component of an algebraic set. Tognoli proved it's a whole algebraic set. But the rest of there are many wrong proofs, wrong papers in the literature. And then we wrote that Anna's paper with Henry, generalizing this to many versions in algebraic homology, and then doing this in non-singular algebraic sets. And then finally, I mean, there were some improvements. How small can you get? Can you do it right inside of Rn? That was the most difficult thing for us. So that's our final paper on the subject, published in Invenciones. In fact, the referee and editor insisted that the only way he can publish our paper, we should go on the literature, correct all existing proofs. In fact, there was a very well-known journal. There's a proof claiming even much more than this. So that's why our paper in Invenciones turned out to be longer than we wanted, because a substantial first part of it, going one by one, all the previous versions of this was claimed in the literature. We had to find a counterexample and then tell why these theorems are not true. So the meat of the paper, I will explain this today. So let me start with the theorem. A baby version of this theorem, we put it in Anna's paper. So we are interested in embedding like this, M, F. This gives, so you take a map M, V, non-singular algebraic set. Say this defines a Bordism class. M-dimensional Bordism. Bordism is a group associated to every manifold. Elements of this thing are objects like this manifold and a map to this. And two things are equivalent if you can find the cobordism between manifolds and extend that map. So there's a Bordism. And then there's a notion of algebraic Bordism. In that case, these elements are, this is a non-singular algebraic set. If this is a non-singular algebraic set, and this is an entire rational function. So those elements are called algebraic elements. So the theorem is, so this is in general Bordism class like this. So MF is an algebraic Bordism if and only if F cross 0 can be isotope to a non-singular. For some n. So this is like the generalization of the theorem on Euclidean space. I mean, this theorem is very difficult proving in Euclidean space, the advanced version, but I'm giving you this version. This is like a baby version of our paper in Anna's. I will prove this right now. So in a non-singular algebraic set, I mean, this is in the Bordism class contains an algebraic representative. Then F can be isotope the algebraic subset of V cross Rn. Proof, this is a proof. Proof with pictures. So this is my board. This means living in this means this can be worded to some other manifold and non-singular algebraic set and an algebraic entire rational function, and then a map like this. So I draw. So let me draw a picture of this. This is my M. This is my M. This is my W M plus 1, and this is my non-singular algebraic set. This is non-singular algebraic set. It's a Bordism, and then that map here, F, extends like this. This is rational, anti-rational. Here, with pictures. So Bordism class contains algebraic representative. What you do is this. You take this, cross with this I. So this thing is now W cross I. You cross this I, and then that extends this map inside. In particular, you have a map on the boundary. Let me call this boundary. So just take the boundary of this. And then you have a map from here to V, and then manifold sits in here, M. Call this thing, this manifold is, I don't know, do I have a name for this? Zm plus 1. So Zm plus 1. So I produce one higher dimension manifold. Inside of this sits my manifold, and then some non-singular algebraic set, and here, sitting in here. So you should see this picture of it. You know, this is my picture, Zm plus 1. I have sitting as a codimension 1 submanifold M. In this, it is homologous to some algebraic set. Yeah. Remember, I prove a theorem that codimension 1 submanifold of algebraic varieties can be isotope to algebraic subsets if their homology contains algebraic representative. Here's an algebraic representative of this homology. I mean, this was in HM, and this is in HMA. Zm plus 1. So therefore, M is isotopic to an algebraic subset. So in particular, I mean, this map, I also have a map in here to V. Is this clear? I proved this last time, and now it's an application. I mean, this theorem is much more advanced that I'm mentioning, but here's you can give a nice, easy proof of this version. So here's a fact. I will come back to that fact. I mean, Bordism class of a smooth manifold is isomorphic to homology of this smooth manifold plus Bordism class of a point. It's a Thom's theorem. So to get algebraic representative in here, I mean, these are all generated. These are Bordism group, cobordism group. This group is generated by algebraic subsets, algebraic sets, projective spaces, take product of projective spaces, take some hypersurfaces in it. So this is known to contain all elements here are algebraic. So to say that something in here, a class is algebraic in here, is really equivalent to saying that the corresponding things in here are algebraic. So I could have just mentioned this theorem. Every such map can be made algebraic inside of V cross Rn if V has totally algebraic homology. All the Z homology classes are algebraic. that would imply, so this, if this is total algebraic homology, means I can put in here, this will make it with A. Yeah, okay. So a few facts about this algebraic homology. Any questions so far? So we say, so the definition, just reminding you, V is total algebraic homology. If V has total algebraic homology. So this is remark. If Bordism of this is isomorphic to algebraic Bordism. Okay. So since I've been using this algebraic homology, I should give you some general facts in case you want to go in the literature, read about them. There's a lot of interesting facts in here. Let me mention two facts. Not every closed, smooth manifold is diffeomorphic to now singular which has total algebraic homology. This is the theorem of Benedetti and Dedo, I believe. This is the, I mean, if you, even you change algebraic structure, you put some algebraic structure on a manifold, make it non-singular algebraic sets, you may not be able to make all homology generated by algebraic subsets. There is some obstruction coming from characteristic classes. Chern class, you know, is related to Stiefel-Whitney class, and then you can find some very cyclic manifolds you obtain from Eilenberg-MacLean spaces. Stiefel-Whitney class don't satisfy the ones that you can get from here. This is one characteristic class obstruction. There's another theorem I prove with Henry King, which also appeared, I think, in Invenciones. This is kind of an amazing theorem. Every closed, smooth manifold is homeomorphic to an algebraic and algebraic variety with total algebraic homology. Here's a non-singular algebraic set is homeomorphic to, you know, algebraic set or algebraic variety. No condition about non-singularity. So smooth manifold can be homeomorphic to an algebraic set. All the algebraic homology is represented by algebraic subsets. So there's some deep connection with smoothing manifolds in algebraic cycles, as you can see, up to diffeomorphism. So there's some, yes? Second remark is every closed smooth manifold is homeomorphic. This one? 1, 2. Yeah, so you can, you give me any closed smooth manifold. I can construct an algebraic set, okay? which is homeomorphic to this. All the homology is generated by algebraic cycles.
Oh, okay, sorry. My question is not, I didn't state that.
This is with the result of Henry King.
Okay, when you say that a smooth manifold is diffeomorphic to an algebraic set.
Yes, homeomorphic to.
A non-singular algebraic set.
Yeah.
You mean smooth?
Smooth, yeah,
Not
smooth.
homeomorphic.
Right,
Okay.
right.
My second question is, for the second remark, do you have any example in low dimension? I mean, it's possible to see.
Second remark, everything, every closed smooth model on this one.
Yeah.
So let me construct you an algebraic set, non-singular algebraic set, which doesn't have total algebraic homology. I will demonstrate to you, and then I have to prove that you really are looking for not just any algebraic variety without total algebraic homology. You want to some smooth manifold, no matter what algebraic structure you put on it, smooth algebraic structure you put on it, it will not be total algebraic.
In low dimension, we have an example.
Yeah, you can find the example. They will be some skeleton. You take some skeleton of Eilenberg-MacLean space, put in Euclidean space, take a tubular neighbor, double them, something like this. But I think it's more pleasant to see your first example of a simple examples, lower dimension, whatever, non-singular varieties, which don't have total algebraic homology. So let me just, since you mentioned, do that in here. So here's a fact. This appears, I think, reference number 22 in my website. This version for all k, where x is a non-singular compact algebraic, the non-singular algebraic set. You can make it compact if you want. V with hk is not isomorphic to hka. I mean, I used to think about these examples, just daydream about this. Can you complexify them, relate to the Hodge conjecture, whatever. Hodge conjecture is about homologies that cannot come from algebraic cycles, but those are complex objects. So here's an example. So you take x2 to the 4, you want concrete example, plus x1 square minus 1, x2 square, x1 square minus 4 equal to 0, and then x3 is equal to x4 equal to xn equal to 0. This is just the plane curve I mentioned before. I mean, this is just the plane curve, irreducible plane curve. It has two components, irreducible algebraic set. So this you cannot have this in complex category, but this is a not connected object. It's in rational components and irreducible, yet it's irreducible. So that's the equation in here, x1, x2. Then I'm crossing this with r to the m minus 2 here. Okay? So let's do step by step, which everyone can understand. So my first attempt would be take a manifold, which is that circle, one of these circles. Can I make that algebraic? Can I assume that is algebraic? Of course not, because if this was an algebraic, and this is an algebraic, difference will be algebraic, and this will be not irreducible algebraic set. So you cannot assume one of these things algebraic. But homology has to do with, we're moving around. Can I, from this, can I cook some better examples? So there's a picture of my manifold. Call this manifold Qm. It's M manifold, very simple M manifold. This is my Qm. I will draw these as 2 points. So call this x0, x1. 2 components. So this set is X, irreducible algebraic set. So I draw them like 2 points, x0, x1. A schematic picture of this. I want to make this this thing kind of stable. Even if I move, the homology cannot be algebraic. Well, what I do is I put a smooth manifold of any codimension in here. So in there you put a M, I don't know, so M minus R, codimension R dimensional. So M closed smooth manifold. Now I know I cannot make M non-singular, I cannot move this thing, a non-singular algebraic set, keeping this fixed. If I can, then intersection of 2 algebraic sets are algebraic. This one and these 2 things, 2 algebraic sets, the intersection will be this. This will be one of the components will be algebraic, but it's a irreducible algebraic curve. But you still object. I mean, this moving M, keeping x1 fixed is not an algebraic geometry problem, right? This is some topology description. Tell me some algebraic cycle cannot, homological cycle cannot be algebraic. Okay, so I go one more step. I blow up, so since this is an algebraic, this is an algebraic set, one-dimensional algebraic set, I blow that up. So, with the color, I blow. So this is a X blown up. So when I blow up this was, I mean, each circle was, inside of QM, each circle was, S1 cross Rm minus 1. This is neighborhood. When I blow this up, I get some closed objects, and they each becomes, when you blow up this thing inside of a QM. So I'm really blowing up this X inside of QM. So each piece will be S1 cross RPM minus 2. So these are my blue things. This is a blown up thing. Blown up thing. Now I have, when I do that, I have this M, strict transform. So M was intersecting, M was going through like a torus going through this, containing both of them. So when you blow them up, you blow up M. It's a strict transform. Now I'm in a stable situation. I can claim that you cannot move these things, M. Now it's a smooth manifold. You cannot move the smooth manifold in an algebraic set. Why? Because if I could, there's a map in here. Map in here. The intersection will be codimension 1. This is a codimension 1. Each codimension 1. 1 inside of. So, in fact, they are just S1 cross RP2. disjoint RP, RPM minus 2. So sitting codimension 1. If you like, you can cross this with R again. So this is a blow-up map. Now you look at Q tilde cross R large, Rn. When you do this, these blue things also gets multiplied. These are codimension 1. Or two components. And then I had in yellow in here. I mean, this is now in here. My this M tilde sitting in here. M tilde is like this. Now I claim this gives us some homology class. I claim this homology class cannot be algebraic, because if you can move this in algebraic homology class, then you would be if algebraic, if it is moved to an algebraic class, it means you just perturb it to algebraic class. This intersection will be algebraic. So, and we call this intersection Z. So Z is Z in this case. I don't know, let's call this P multiplying with Rn. Call this blow up pi. So Z is, this is a Y. Suppose I move yellow until that algebraic set. So this is Y, algebraic set. So you get Y intersect I P inverse of X. So these are the blue ticks. So if you do that, then you get a map here. You get a map called this capital F. What's the property of this map? Well, this map is mapping from this algebraic set Z onto here exactly. Because no matter how I move this corresponds to moving this. Corresponds to moving that in here, corresponds to moving that, keeping that fixed. So then I will get a degree 1 map from an algebraic set to an algebraic set. And then this will be like X1 is going to be image of Z. It's an algebraic degree 1 polynomial map. You can never have such that this thing, Zariski closure, you cannot have Zariski closure same dimensional. Remember, I told you if you have a degree 1 map, I think I told you like this. What is F inverse of a point? This is a bunch of RPSs, some projective spaces. Because if you blow up, if you take a point, inverse image of point in here, will be projective spaces, these things. And then you just get the codimension as you wish, so that they will have odd Euler characteristic, for instance. Then you would have a map from this algebraic set Z to here, to this algebraic set, such that Zariski closure is X0 union X1, same dimensional. Fz is just X1. So that's a violation. That's the theorem I mentioned last time. You can't have a map like this from algebraic set to an algebraic set. Euler characteristics of inverse image of points are Euler characteristics. So in particular, degree 1 in Z2, with Zariski closure contains this. Because the Zariski closure of this one of the circles is the other one together. And it has to be lower dimensional. So by changing the values of M and the manifold you put in there with M, you can generate enough of these for each K. So okay, so this. Any questions? I mean, I really want to say that you cannot move this yellow to algebraic set keeping that fixed. So if I could, then I take intersection of this algebraic set and this, I get a contradiction, one of the components algebraic. But it's not natural. I want to put myself in a situation, no matter how I move, not just keeping this fixed. That's equivalent to saying that like this, no matter how you move, that means when you move this algebraic set, that corresponds to moving this, keeping that fixed. Here. Okay, so tomorrow I will talk about classification of algebraic sets with isolated singularities, and then that theorem also requires the relative version of Nash theorem. So now we learned that if you have an unsingular algebraic set, a smooth submanifold, there's no way you can move that algebraic subset even when you cross with Rn. If it has total algebraic homology, you can. There's a theorem. And but if you have a submanifold of an algebraic variety, if you are willing to change algebraic structure, find another algebraic variety, non-singular algebraic variety, diffeomorphic to this, such that the submanifold corresponds to a non-singular submanifold, that you can do. So let me put through the theorem. This is the main theorem in our first annals paper. If you take all fancy stuff out, the simple version is this. If K closed smooth manifold these are transversal intersecting submanifolds, then I can find the diffeomorphism is to non-singular algebraic set. Transversal intersecting non-singular algebraic subsets. You can consider this as a relative version of Nash theorem. This is very important. This is almost equivalent to classifying algebraic sets with isolated singularities. And let me prove codimension 1 case. So if I give you the proof of codimension 1 case, you can go and read the paper, general case, basically generalizing these ideas. So I'm taking this, so each codimension 1. Okay, so first of all, so this is my manifold, and I have a codimension 1 manifold M1. You can find the map. You can find the map gamma, so MI, gamma I, RP, and everyone knows this because this approximates to KZ2, KZ21. Homotopy class of maps to KZ21, one-to-one correspondence with one-dimensional cohomology. So take the finite skeleton of this, and such that then you can do this such that gamma I transversal to RP n minus 1 and gamma I inverse RP n minus 1 is MI. Okay, so you do this for each MI. So then you write M to gamma, product of RP and I's, bunch of RP and I's, which is like gamma 1. How many gamma K? Such that when you project this, project to I factor, I don't know what to call pi I, it's RPN. So from this construction, pi I omega I. So, and then there are all these projective subspaces, RPN minus 1s. So you make them transversal. If you pull back all transversal inverse images, you will see this picture. Like this. Now, this is my V. This is my V. Now I appeal my big theorem. This is a non-singular algebraic set. Projective spaces are algebraic varieties, non-singular algebraic varieties, with total algebraic homology, because all homology is generated by subprojective spaces. Therefore, I'm able to turn this into algebraic subset if I stabilize this. So therefore, this total algebraic. Therefore, I can make this a non-singular algebraic subset. Inside of Q. Yes. And then again, if you project this to pi I, I'm still the pi RP and I. When you just project this, pull back this subprojective space, you'll get one of these guys. Okay, so now it is algebraic subset V. So I turn this thing into V. So I have a V, and then V from Markov notation. I'm calling everything pi I. So then you just take VI. VI's are pi I. You project this, and then you pull back. So you turn this situation into this situation. V1, V2, Vk. All non-singular. Of course, I cheated. I took everything codimension 1. But having seen this, you can go to that paper, our first paper. This is a funny story with our annals paper. We are junior mathematicians. We submitted the annals. We waited 2 years. Our paper rejected. Henry told me, just divide this paper in 3 and then submit to annals. So we divided in 3. Send one, they didn't even know. We submitted one portion to annals, one portion to commentary, another portion to transactions. Out of it, we got 3 papers. So this is a good lesson for us. And it started with some explanation like this, and then working towards it. And we were just foolish enough to try to make a more sophisticated proof. It's not a good idea always. Okay, now I think I will use in classification of isolated singularities this theorem. In fact, it is enough to know this codimension 1 case if I want to classify algebraic set with isolated singularities. Any questions so far? So So now I come back to our fundamental normalization theorem that I will generate everything from that theorem. Okay, so what did I have? I have a smooth manifold, and I have a map, some algebraic subset. Now, right now, I'm aiming to make a smooth submanifold of Rn algebraic without stabilizing, doing anything. But just think, it's better to think more general situation. I had this situation, and I found a diffeomorphism, if you remember. There was a diffeomorphism, and then in non-singular algebraic set, component of a non-singular algebraic set, and then I had a map from here to there. Now I'm interested in only a Euclidean space. Let's make this simple. Let's put this Rn, and then this could be emergent, but let's make it embedding. I make it a baby case, and then my theorem. Remember, I had a picture like this, normalization like this. I end up getting a polynomial map like that, phi, okay? And that was, in my situation, this was a component of a non-singular algebraic set, my normalization theorem, and a map like this. And then f was close to phi, this is diffeomorphism. Now I'm praying that once I do this, now remember I applied this to many situations. I took V to be Thom space, Grassmannians. I generated all those theorems. Now I'm go back and apply this theorem, more fundamental case where the target is just Rm. And then after I did this, I'm hoping that image is non-singular algebraic set, then I'll be finished making a submanifold of Rm algebraic. In fact, this is a source of many wrong proofs in the literature. They didn't even have that normalization theorem, but still they were putting something, taking the image and then hoping that that will be algebraic. So it's not going to happen this way. So what you have to do more sophisticated. It's an algebraic set in Rk. So let me go by step by step. Remember, I just proved to you, if a Bordism class is algebraic, you can make it a non-singular algebraic subset. So if you translate to this language, I can even take this to the whole algebraic set. Because I was proving whole manifold can be made non-singular algebraic set. If this Bordism class is algebraic, I mean, this is a Bordism class of Euclidean space, right? So trivial, and there is no Bordism condition. So therefore, by that theorem, I can even assume this is not just a component of a non-singular algebraic set, whole algebraic set. Now I want to do something, I mean, image still may not be an algebraic subset. I don't know what it is, so take this image, phi z, I have no idea what it is. Take a Zariski closure. So that sits in Rm. Okay, now I want to get some help from complexification. Now this sits inside of a non-singular algebraic set. Here. In fact, you can assume that complexification is non-singular. Even though I have to warn you, this is one of the examples I will mention to you, that there are examples of smooth manifolds, even in projective space. They can never occur to be smooth parts of, real part of non-singular complex varieties in CPN, even though they can be isotopically non-singular subsets of RPN. So that's a phenomenon about about transcendentalness in the even smooth category. But here, you are only taking, I mean, you can adjust this to get this non-singular here. Okay, so And then you can look at the image. Because this is a define over. I mean, this is a map from R, so this is like a polynomial map. You just look at the map induced in complexification. So then I look at the phi CZ. So this sits inside of that. Let me give a name. Let me call this a Y. Okay. If this is proper, there's a theorem about complex algebraic geometry. If you have a proper map, image of a complex algebraic variety under a proper map or a finite map is an algebraic subset. So this is an algebraic set. This is algebraic. So this is, I will call this X. And this is sitting in here. Okay? And this is sitting, again, to emphasize it, this is Rn, this is Cn. So my goal, let me tell you my goal is to realize this thing as a, this is a closed smooth manifold. So this is a closed manifold with a non-singular algebraic structure. My goal is to this map to one of the component of this as a whole non-singular component in there, so that I will get that smooth manifold can be moved to non-singular points of an algebraic set. Not that just the whole topological component, but whole non-singular subset. The other things are little microbes away from that. That's what I want to get from this situation. Okay, is that clear what I want to do? So first I need to get this to be proper. Okay. And the first question is, this since this is an embedding, so in the Jacobian is non-zero, and this is a diffeomorphism. This is a Jacobian as non-trivial. So this is an immersion. In the immersion case, it has a smooth manifold. It maps smooth points to smooth points in here. So this is a non-singular complex variety because it's a polynomial map defined over R with the Jacobian condition, a non-vanishing Jacobian. First question is, what is this relation? I have a complex algebraic set and then a real algebraic set there. The question is this complexification of this, is Y real part of X? We need to analyze this. So the goal Y. Because I took a Zariski closure, it's an algebraic set, so it will be like algebraic set like this. So Y will be like this. Y not will be like this. This is my ultimate goal, to prove this theorem. Let's play with this a little bit. Of course, this is not going to happen. It's just pipe dream or something. You need properness in here. You also need, because this is a complexification of Z, when you complexify it, then you look at the image map, a real part, that complex points might come to real points. And then you might have this kind of things appearing under this. So you want to prevent all this points from complex parts coming interfering with your manifold. So for this, you need phi inverse phi z is equal to z. This is need. This might look like I'm asking too much. So there's a phi in here. When you take the image of this, take the inverse image of it, you might have complex points. I mean, maybe I should put C here. Phi is equal to phi C. Not the allowed to notation. Okay, so let me work towards here. So assume this, assume this, assume this, and let me solve this problem of this guy. This was my ultimate goal. Write my smooth manifold as a smooth points of an non-singular algebraic set in Rn. Okay, so let's play with this. So first step, I want to prove that X is a complexification of Y, and Y is a real part of X. So what is this? Y is a non-singular algebraic set sitting in this algebraic set, complex algebraic set, sitting in the real part of it. So it's clearly, I mean, it's sitting in XR, so therefore sitting in X. So if I complexify this, I mean, if I complex, this is a complex. So if I complexify this, complexifying means smallest complex algebraic set containing it. It must contain this. So this is, I prove this one. So this is number one. Number two, I have Z is inside of phi inverse phi Z. Okay, because it's obvious thing here. So this is phi inverse of Y. Why? Because this guy, because Y was the Zariski closure of this. Remember, Y is Zariski closure of this, bigger than phi Z. So I replace this by Y. Okay? And therefore, and this is included in Y of C, complexification. So Z is inside of phi inverse of Y of C. Oh, I'm sorry, there's this phi, there's a phi. I'm just replacing with something bigger. No, I think phi inverse Y of C. Okay, so then X, I have X is phi of Z C. That's what it is. Because ZC is contained phi inverse of Y of C, because ZC is a complexification of Z, but there's a complex variety containing Z, so that must be smaller than this. So I mean this. So that's what I used in here, and then this is in Y of C. Because I keep using this. And this is inside of X. So I mean, I have just inclusions. So therefore, X starting with X, ending with X, Y of C. So conclusion, X is Y of C. Now I related this natural complex variety is a complexification of this Y. It just points at topology. So now the claim is, any questions so far, since it's a class? So I'm using two assumptions, this one and that one. So this is what I want to show. So phi sits inside of y0. So phi is mapping into y. Y is an algebraic set. Since this is immersion, it maps in the smooth parts of this, which, let me call this y0. This is smooth parts. I want to show this inequality. It's not just inclusion, it's inequality. The fact it's an inclusion because it's an immersion. It has to, it takes the smooth. This is a smooth non-singular algebraic variety. This is an immersion. It's going clear inside of a non-singular points. Non-singular points might contain other things. It could be bigger, I don't care. But suppose not. If not, there exists x, y naught minus phi of z. I mean, this is closed. Image of closed set is not closed, but remember, it's a proper map. Phi is a proper map. So there exists open set. And remember, this sits inside of y naught. I mean, anyways, from here, dimension of y naught minus y minus is m. If you take a dimension of this, dimension of y is same as y naught, non-singular points. And this is m because I found an open subset in here. So I have a map from Z to Y, phi, this map. Degree 1, because it's a diffeomorphism going into diffeomorphism, degree 1. So therefore, dimension y minus pz less than so when you have a degree 1 map, this Zariski closure of what is added is a lower dimensional. Right? I mean, this is the Zariski closure. Of this, right? I mean, Zariski closure of this. Remember what I proved. If you have a degree 1 map, you take the image on the polynomial map, and you take the Zariski closure of it. New added things are lower dimensional. But then this contradicts in here, basically. Contradicts. I intentionally skipped some steps. I wanted to give enough details so that you can go read this. That's exactly the idea. And now, my goal is, this is my basic triangle. A smooth manifold map, and then this. I want to set this triangle such that this will be proper, and then I will have I will have, what's that condition? Phi inverse. In this condition. It looks like this is too hard to satisfy because you map this, and this is like phi c. Here. You map the real part and take the inverse image, and then you might have new complexes, points appearing. And then I need to do that. So this was some technical discussion to see where we are going. Any questions so far? So I will have here, I've written two things. One, to make this proper, and then two, to jiggle phi such that satisfy this. So theorem, given f m to v in this case Rn. I can find a non-singular copy of this m. I will always start with this, diffeomorphism to z, and this is inside of Rk. This is non-sinc. And this is my map, F. In my case, is an inclusion to Rn. And this is sitting inside of Cn. And this is a complexification Cc sitting inside of Ck. And then my basic theorem gave me a polynomial map rho, and then that has come with complexification map. And this map is really defined over R, it's just natural extension to this. And the condition was F rho phi was approximating F. That was condition number A and B. The finite map, you know what finite map is, right? The inverse image of points, finite point is a finitely many points. In particular, finite map is a proper map. And that's C. So Z is union of connected. Basically, I want to do the same thing. I want to make Z is a union of connected components of a non-singular algebraic set. In here, I'm describing it like this. And then I solved one of the problems. I made this finite. And then this was always, I always have that. I don't know, for instance, A plus B in plus C. Let's prove this one. If you have finite regular map, for instance, Z sits inside of rho inverse C Rn. So this is closed, right? It's a closed subset. Why is it? I mean, this is also, I mean, it's a closed subset of this guy. Why? Because Z is an image of a closed manifold. So this is a closed set. It's also Z is an open set in here. It's also open. Because Z is, because immersion, set of points is a union of open sets. They are all going in there. So it's an open closed set. So it has finitely many components of that. So I need to make this map finite. Well, I mean, there are theorems in algebraic geometry how to make finite. If you have an algebraic variety, I think in n-dimensional algebraic variety, complex algebraic variety, there's a generic projection. You can take a generic projection to some hyperplane and then to make this map finite. So now I use that. So you can assume this is non-singular. I mentioned before, when you complexify non-singular algebraic set, complexification assumes non-singular. If singularity appears, you know what to do, right? You send it to infinity. T times, you put a new coordinate, T times equation of the singularity equal to 1. So you do the same thing in complex category too. So, I mean, you have this Z, you have this Z, you have like this. You can, you can send those to infinity. I mean, the ZC you can always assume non-singular. It's in the book as a lemma, but you can do it yourself using that idea. Okay, so you define so I want to solve this, prove that theorem. To prove that theorem, I do everything from beginning. I have an M, I have a G, I have a non-singular variety, and that's sitting inside of a singular thing. And we call this RK, CK. Sorry for writing this again, because I will, from this I will obtain that one. So I have a map in here, F, Rn, sitting in Cn, and this is my phi polynomial map, and then I also have phi C. I'm same thing except letters, name of letters change in here. You start from there, make so I want to make this map finite by doing some trick. So you define the following. Z is, you just graph this. This is a common technique that we use all the time. Every time you have a map, one algebraic variety to another one, by just graphing, you can assume that map is projection or inclusion, and everything gets simple. So you are just taking the graph of this, and then this has a complexification, xy, xcn, y, because phi is a real polynomial. Okay, and where is that sit in? Where is that sit? This sits inside of ck cross cn, because this sits inside of rk cross r, because x was in rk. Okay. Now you have this is a complex algebraic subvariety. Now you go open in Safarevich book or a Mumford book. It says that you have an algebraic variety like this. There's a generic projection generic linear projection close to standard projection, Cn, such that when you do pi less equal to Zc, this thing is finite. So I'm going to go this thing and put it in here. So the way you do this, so you take M. So I want to change the situation such that this will be a finite map. So you map it to Z. Now I replace X by Z. I mean, clearly this is diffeomorphic to X as an algebraic variety. There's a graph of that. Okay. Sits inside of ZC. So you map this by G. So I had a G, and then so the Z, but the Z has two coordinates, right? Z has two coordinates. This goes by G, and this one